Okay, everyone, as I wrote here for Makeup Quiz 3, since it's online, just email me and tell me when you want to take it. You should give me an hour that you want, or a time specifically if you are allocated more time for your homework. Anyway, you should let me know, for instance, can I take it Monday at 4 p.m.? And I'm sure, I say sure. I program it somehow that you can take it at that time. And for Makeup Exam 2, I'm going to proctor them next Friday, 3 to 4, 4 to 5, 5 to 6. And if none of these work for you, email me and I try my best to accommodate you. Questions? And as we're getting towards the end of the semester, so try your best on your homeworks. Homeworks I don't provide makeups, period. Unless you give me a heads up in advance, tell me that, I cannot take it for this reason, right? It should be an excuse reason. Other than that, I don't write a makeup because you can easily improve your grade. One of your friends, they got 12 out of 20. They came to one of my tutoring sessions, they got 7 points. That now their grade is 19. So it's easy to compensate for those points. So just by going to SI Pass tutoring myself, you can just compensate for those. And I cannot guarantee that if you mess up exam 3, it would be a makeup because you have several courses, I have other classes, we are all busy. So try your best to do well on your exam 3 because necessarily it won't be a makeup. If you struggle and then we have time and then you tell me that you want to have makeup, I may accommodate that, but most probably if you don't do well on the first one, based on last semester experience, your grade won't improve much in the second one, in the makeup one. So do your best for makeup exam 2, and you have next Friday your quiz 4 due as well. And this is not my fault that we're doing makeups. I'm trying to accommodate you, right? So help you, but this is how it is. So at 11:59 p.m. you should make sure to also do your quiz 4. So you should put lots of work. With that being said, I'm going to start chapter 9. And anything, students email me that, what did we talk about in this class last session? That's why I upload the lecture. So if you miss the lecture, and if you just look at the PowerPoint slides, probably you cannot understand all the materials. Even when here I'm trying to, I'm doing my best to teach the materials, I'm having difficulty to convey the information to you. So if you just read the slide, most probably that cannot be achieved. Any questions? And maybe you think that this is a big class, so I cannot see you. I see each and every one of you, right? people who watch movies, people who read novels, people who play games on their phone, people who are doing their homework for their next class, everything I see. As long as you don't distract me or others, that's fine. This is your grade. Eventually, I try my best to help you, but eventually it's your grade. But I cannot tolerate when you're distracting others. So please don't do that. Chapter 9 is about electrons in atoms and the periodic table. And we're going to talk about quantum mechanics in this chapter. And I always, when I'm explaining some material to some of my friends or family members, we have like this expression, and it might be, you may use it here too, but in Iran specifically it was like so common. I'm not talking quantum mechanics. It's something, I'm saying something really easy, it's not nuclear physics. So what I'm saying is that this chapter is about that. So you should study as I'm teaching and then ask me questions. And I'm going to, after being done with these slides, I'm going to also take some screenshots of your book, which is technically illegal because I'm not supposed to do that. But I'm going to have some slides like that to make sure you study them, as long as you don't tell publisher. I don't think anybody cares eventually. But make sure that you study these things. Okay? This chapter is lots of memorization, lots of conceptual problems that I know some of you don't like, but some of you don't like also numerical problems. But they should ask you something in the exam, right? That's why I give a balance. I have like questions that are numerical. I also have lots of definitions, so even if you're struggling with either of them, still you can do decent as long as you study and then go to tutoring, talk with me and all stuff. So the first thing, and I also, as I mentioned, I'm going to write, and I'm writing always, the part of the book that I'm talking about, so you know which part I asked you in the exam, right? For instance, last chapter, we didn't talk about enthalpy reactions and kind of calculating enthalpy based on moles in chemical equations and chemical reactions. So I'm not going to ask you that in exam. As long as you just learn what I taught you, that would be more than enough. So light. When we talked about matter, can anyone tell me what was the definition of matter?
Anything that occupies space.
Exactly. Anything that has mass and occupies a space. Sometimes we can just see it, like this table, I can see. But oxygen in the air, I cannot see, but still it's there. It occupies a space. It has a mass, right? But what about light? Does it take space? Can I show you? Okay, here is light, right? Does it have a mass, occupies a space? No. Light is type of electromagnetic radiation. And I also wrote the definitions here, so when you look at your quiz, homework, and all that, after you study these materials, it would be like straightforward, and then if you have difficulty, you can refer to the slide. So electromagnetic radiation is a type of energy, remember, that is energy, that travels through space at a constant speed of 3 multiplied by 10 to the power of 8 meter per second. And this is really important about light. For the longest, scientists thought, kind of like I tried to underline, but I'm kind of like blocking what I wrote here. Scientists thought that light is a wave. But then they realized, because of some experiments that they did in the laboratory, and then we're going to talk about some of them, but in general, I just want you to know the result. They realized that light can also be considered as particle. So light has dual properties, or like dual characteristics. We can consider it as wave or particle. And each particle of light, we call it photon. And I have it in the next slide. But in general, I give you this and I say, is the following statement true or false? Or I say which of the following statements is correct or incorrect about light. As long as you read this slide, comprehend what it means, you should be fine. And here I just said, right, light is form of electromagnetic radiation. And this is the main subject that we're talking this session. And anytime that I'm teaching, even if I don't ask you any questions, just like raise your hand or just like shout at me, just, you're good at it, so just do it. So wave, what is wave? So your book just wrote that when we have like a stone and then we throw it in water, we see waves. And then, or if we have a rope and then I have like one piece of rope here, here it would be difficult, on this wall. I thought that wall is so far away. But if I have a piece of rope here and I can attach it to this wall or like to this, I wanted to say doorknob, this is not doorknob, but you get the idea. I can attach it somewhere and then I stretch it and then I gave it a movement. You can see a movement that we call that a wave. And I was thinking that how can I convey that better or have like an organized definition in a sense. So I refer to this website like physicsclassroom.com, really legit website. But the definition is correct. I always tell the students that don't just go to Wikipedia or like any random website to go to scientific articles and all that. But these concepts, because they are really well established, it's difficult to find a website. Unless a website that my nephew writes or someone that is like 10 years old, you know what I mean? Most of the time it'll do, because these are like well established definitions. So if we want to put this rope or like these water waves in words, we write a wave can be described as a disturbance that travels through a medium from one location to another. Okay, as long as you know what we mean by wave, you can comprehend what I'm teaching. Is that clear? So you can think of the rope example and also the water that is still, you give, when you put like a stone in it or like drop it, is kind of disturbance to that medium. And then it kind of like distributes. As you see, we have like this wave-like motion here. Now we have one definition here. So we talk about wavelength. So that rope that I showed you previously, or if we have like waves in general, in this maximum that we have here, if you think about this, as your direction of travel, I'm kind of just like highlighting what you already have here. If you consider that, the maximum point that this rope can go, or your wave in general, we call that crest. And then here, the minimum, we call that trough. But what I asked you in exam would be wavelength. What is wavelength? So wavelength is the distance between adjacent wave crests in a wave. It can also be adjacent troughs, right? Doesn't matter. But here, for instance, as we said, each of these are crests. So the distance between these two, we call that wavelength. And as we say, it's kind of length of wave, is length. So it has basically unit of length. Okay? And most of the time when we talk about light and electromagnetic radiation, we're dealing with like photons, as we said, or like really small, things. So that's why we use nanometer. And I have that in the next slides too. Can anyone remember what was nano? Those prefix multipliers in SI units, we had like kilo, giga, those tera. Yes. Was it positive or negative? Negative 9, right? So this is, nano. Like nanotechnology deals with particles that the size is really, really small. Okay. So this is, we have like lots of definitions in this class, in this session. That's why I'm telling you it just needs like lots of memorization. So what was wavelength? What was electromagnetic radiation? What was light? Was it a wave? Was it a particle? What was photon? So it's kind of like lots of definitions. Any questions so far? Good.
What were you saying about nano?
Yeah, great question. So what is the relevance? So here, the wavelength, what I said is that it has the unit of length, right? So we can report it, for instance, meter, or like centimeter, or like nanometer. So instead of reporting this number really, really small, and then I have like the numbers, you know, I have to make an example that makes sense. I just not throw out a number. So if we have this number and I say this is the wavelength of this specific wave, okay? So if I don't want to write it nanometer, I can write it meter, right? I can convert this. We learned conversion factors, right? So if I say how many meter equals 400 nanometer, right? And I say nano, so 1 meter is 10 to the power of minus 9. So this number would be 400 multiplied by 10. Sorry, I did that reverse. So 1 nano means 10 to the power of minus 9 meter. And you know, when you do, make a mistake like what I did, ask yourself, does the number make sense? So how I wrote it before, it was like 10 to the power of 9 meter. That is an extremely large number. And when we're dealing with something really small, photons that are really small, that doesn't make sense, okay? So you can always check your answer. But 1 nano means 10 to the power of 9 minus 9. So this would be 4 multiplied by 10 to the power of minus 7 meter. If I want to write this number, I write 0.000000. So it would be 1, 2, 3, 4, 5, 6, 7, right? Remember how to write scientific notation? We say that here, the implied decimal place is like here, right? And then now I shift it to here, and then I count. Here I want to have like 10 to the power of minus 7. So for instance, if it was like here, it would be 10 to the power of minus 2. 3, 4, 5, 6, 7. So what I'm saying is that what you should need to know, or like the correlation between nano and what I'm talking about, is that writing this number is not the most convenient way, and I should keep track of zeros to make sure I didn't mess up the number, So for that matter, it makes sense that I just say, 400 nanometer. It's just like easier to write. Does that make sense? But remember, wavelength is length. It has the texture of, I guess you can put it, it's meter or like centimeter. It should have units of length. Great question. Any other question? So if you have any question, just feel free to ask me. I don't want anyone leaving the class not understanding anything or like some part of the course, okay? At least these ones, I just want to make sure. Yes?
What was the relevance of nano?
Just one. Okay, now we have another concept here, frequency. So you probably heard of frequency before. When you're changing the radio channel, you go to different frequency to get another wave, And so AM and FM radios are type of electromagnetic radiation that I have in the next slides. We're going to talk about them. But the reason that you can hear them, or like you can change the channel, is because of different frequencies that they have. But what is frequency when I say frequency? Frequency is the number of wave cycles or wave crests that pass through a stationary point in 1 second. What I mean is that if this is the path that my wave is traveling, and if this is my wave, okay, and imagine this being nice and smooth as what your book wrote. So I told you that, this difference or the distance between two consecutive crests, I call that wavelength, and I show that with lambda, okay, the Greek letter. But, for you it's important to know that this is wavelength. Okay. So now we have another definition. It says frequency. It means the number of wave cycles or crests, and it just like whichever you consider, I just say I consider this crest. You can say I consider the number of these, cycles, whichever you want to look at it. Now I go with like this, a specific crest, okay? The number of wave cycles or crests that pass through a stationary point in 1 second. And it doesn't matter whichever point you want to consider. You may say that I want to consider this point, okay? And here, if I have this is like PDF version of my PowerPoint that I imported in this Explain Everything software. So I cannot play a video, but if I had like a PowerPoint and then this was a video, and then you can just, refer to some videos online too, of wave movement. You see that this wave is actually moving. So what I mean is that, if this is an animation, it just goes, right? So you see that this wave is moving, but it would be the same as here, kind of the shape would be the same, but it's basically moving, okay? And then if you consider this point, right, and then you have like a stopwatch, and then just in 1 second, you count how many of these crests are passing through. Okay, we call that frequency. Does that make sense? So now imagine I have a wave that is like, if this is like my travel path, imagine I have a wave that is like this. Okay, do you think which one would have higher frequency? Bottom one, right? This one has higher frequency. Because if you just consider 1 point, and as I said, it can be any point in this axis. Doesn't matter. It can be here, 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 any point that you consider. And then you can count the number of, wave cycles or crests, whichever you're more comfortable. So if it's like this, it's kind of like there are like so many of these waves, there are so many of them traveling. But consider this wave. If I have something like this, do you think which one of these three, 1, 2, 3, which one has the lowest frequency? This one, right? It just takes forever. Not forever, but compared to the other one, it's much slower. Lowest frequency. Now we can notice something here. So here, if I want to report my wavelength, the two consecutive crests, the distance between them, this would be my wavelength, right? Wavelength. Here, the two consecutive crests would be here, right? Wavelength. TH, okay. Which one, 2 or 3, which one has highest or like longest? Because it's like meter or like it's like length, I say longest. But if I say higher, you should, it means like bigger in magnitude. Which one has longest wavelength? 3, right? It's kind of like I try to exaggerate the example so it would be kind of obvious. So here, this one has longest wavelength. Which one has, between like all 3 of these, I guess, which one has the smallest wavelength? 2, right? Then the smallest wavelength. Can anyone guess, based on these examples that I wrote here, a correlation between wavelength and frequency?
Shorter wavelengths, larger frequency.
Exactly. So they are oppositely connected. So when you have, and then in the next slide, I teach you about different types of electromagnetic radiation. And this is one type of question that I asked you in exam. Which of the following has the longest wavelength? Or which one has higher frequency? Those types of questions. So you should remember that when we have higher frequency, it means that there are so many waves passing through that point. So it means that the wavelength should be really small. And then reverse is also correct. When we have like a really long wavelength, less of them can pass through a stationary point. So the frequency would be really low. Any question about this? Good? And just know me. Okay. And this is something that I told you before, so I just wrote here that a particle of light is called a photon. And this class at the end, and also next class, we talk about photons more, so it makes more sense. But as of right now, just remember the definition, that a particle of light is called a photon. And we can think of a photon as a single packet of light energy. So we have like these photons, and then each of them has like packets of energy. And as I said, I'm going to talk more about photons, and they make more sense. As of right now, just remember the definition. Good? Okay. Now I just threw some definitions at you. Now we want to kind of like make more sense of them, or like know why we studied them. Okay, so what? Do we study rope in this class, or like, water? So what is going on? So here I have like this picture from your book that shows us the components of white light. So if we have a light source and we pass it through a slit, and then we pass it through a prism, right? You can see different colors. Have anyone ever saw something like this? Right? So have you ever thought, why is that? Isn't it like just we have like, white light? Isn't it just like one light? Why do we have like different colors? Why is that? Yes. So we have, these constitute of different amount of energies and also different wavelengths. Okay. So each wavelength, we see with different color. And here, if we do this experiment, that passing the light through a prism, we can see, the constituents of white light. And this is what I asked in exam, one type of question. Which of the following is not a constituent of white light? And then when I go through next slides, you see what is not. But as of right now, these colors, you see like, I would do different colors, but it just takes forever. If I want to do red, orange, yellow, green, blue, indigo, violet. It's kind of like rainbow colors, right? And you should know the order. And if you think of it, here, if you start from red has lowest frequency and longest wavelength. And you should remember that. Okay. Violet has highest frequency and lowest or shortest. Again, I say short because it's like length, but anything that shows lower in magnitude. Shortest wavelength. Okay. And something else that we're going to also talk more as I go, through the slides. Also, energy, has the same correlation with frequency. So something that has higher energies also has higher frequency. So if I ask you which one of the following has the highest energy, red or violet? Violet, exactly. When you have higher frequency, you have higher energy. And here it's kind of like, if you look at it in an artistic way, I guess. Here red, the color next to it is kind of, orange. And then orange, if you kind of like decrease the amount of red, would be yellow. And then yellow, if you add a little blue in it, it would be green. And then green, here, after green, you will be having blue, right? So it's kind of like here you have like, red, and then you kind of like decrease the red and then add blue, as I said. And then after blue, you have indigo and violet. So I guess it's continuous spectrum that you have. And does anyone have difficulty remembering the colors? I think this is kind of straightforward, but if you have like questions, just feel free to ask me anytime. But you should know that red has like longest wavelength, lowest energy, lowest frequency, and I add like lowest energy here too. And then here I write highest energy as well. And then anything in between. So here energy is increasing. And then you can say wavelength is decreasing. Okay, and then you can compare any of the two colors that I give you. Good? Here I have like, 10 to the power of here. So here I have like the wavelengths in meters. Where is it? Here. Okay, here for instance I have like 400. Okay, so that was visible light or white light, which is like this small portion. So here your book has like the whole better demonstration, but this is like a small sliver part of electromagnetic radiation. And these are not only good for, we had an expression in Iran, we would say, especially people who were religious, they were like, this is good for this world, also the other world after you die. So this is not only important for your class, this is important for your life as well. So it's good to just like learn these things. So electromagnetic radiation, how many of you ever broken any part of your body, or like you had to take some, X-rays, for instance, right? I remember I broke my elbow when I was 13 years old, and then I had to take pictures of my elbow every week, and my mom was so concerned because X-rays can cause cancer. So if, reoccurrence, exposure to them. So what I'm saying is that, for instance, X-rays, that's why when you take X-rays, or someone wants to take, X-ray from any part of your body, the technician goes out, right? If they just stay there and then they do that like hundreds of times every day, God knows what happens to them, probably not a good thing. So that's why we have like protocols and all that. So you can remember this thing that I just said here to know that X-rays are bad. So we should be in direct contact with them, and we should try to not injure ourselves as much as possible. But if just like, as I said, I'm fine too. So if you have to go to doctor and do something, don't, do that not to go to doctor because I said X-rays are bad. No, if you just go 1 time, 2 times, 3 times, just like, doing it for the medical purposes, that is fine. But the technician, they should go out. They shouldn't just do that all the time, So remember that this is bad. Why is it bad? Because it has high energy. Okay? And the worst electromagnetic radiation, the most dangerous one, is gamma rays. This is like, I'm going to write it like this, as I said, because at this point, I just care about your health more compared to the lecture. So this is the most dangerous one. Why? Because it has highest energy. So if you go to a laboratory, I don't know if anyone here uses gamma rays, but if you see that they have sign of gamma rays, or they need like special clothing, or they need training for people going to the lab, just avoid it, because these are really dangerous, and not only they cause cancer, they damage biological cells. So these are like the most detrimental ones to human and animal health. Okay, and then X-rays we just talked about. I'm not gonna tell you more stories. So you got that these are not good. Okay. Excessive exposure to them can cause cancer. What about UV? Can anyone, based on your daily experience, give any comment about UV, ultraviolet?
Wear sunscreen.
Exactly, we wear sunscreens, especially when we go to the beach, because we don't want our body be exposed to UV, right? And then there are like even some of my friends that they say, even in the room, you should wear, sunscreen because of the light, So, I'm not saying that is not valid, but at some point we just should live our life, we cannot just be concerned. But some stuff that are, we know that we should wear sunscreen when we are just in sunlight. And then there are like some parts of the earth that the angle of the sun is different, and then the UV would be more or less depending on that. So, and then we have like different creams that they have like different levels of protection against UV. So here UV is not as bad as the other two. It's not like that if we go under the sun or if we go to beach one time and then we don't wear sunscreen, something bad is gonna happen to us. But if someone has a habit of going to the beach without sunscreen, just really excessively, it's possible that they develop skin cancer. So UV is bad too. It's not as bad as the other two that we talked about, but it still is bad. That's why we have sunscreens, okay? It's not just because of profit of pharmaceuticals. It has actually a reason. Okay, so here, again, this one is high energy, but I write lower than X-rays and gamma rays. Any questions? So far, if I ask you in an exam, which of the following has the highest energy? Gamma, UV, X-ray. Gamma, right? If I tell you which of the following has the longest wavelength? Which one? Yes, so in general radio waves, but if I say between these three, between gamma, X-rays, UV, which one has the longest? Which one has the longest wavelength? So you can say longest wavelength. So if wavelength is long, it is high, so frequency should be low or energy should be low. So between these three, which one, or even between these ones, you can say energy is low. It means that it's not that dangerous as the other ones, or less dangerous. So which one? UV, right? So hopefully I try to just like give you clues to first of all remember these things, and also, as I said, these are like important for your health too. That's why, chemistry is not just like making your life hard and difficult. It's also, help you in daily life. So now ultraviolet, and this is how I try to help you to remember this. We have here ultraviolet, and here we have violet invisible light. Remember the rainbow colors that we just talked about? We had violet that had the highest energy in white light or visible light, right? So here you should remember that we have violet and we have visible light. And then what was the end of this visible light spectrum? Here. It's red, right? Can everyone see that? Just like your book's color is even like better than what I'm writing. The end of the spectrum for visible light is red. So the next one that we have here is infrared, IR. Have you ever heard of IR cameras? They take pictures, and those pictures depict heat. So that's why if you have an IR camera, even at night, you can take a photograph, and then it shows that where are humans or where is like just objects, because our bodies generates heat, and your book has like really cool images. I include those in the next presentation. But as of right now, remember that after UV is ultraviolet, you have violet in, let me go back to my violet color here, invisible light, and then you have like your spectrum, invisible light or like white light, and then you have here red. Okay, and after red you have infrared, right? It has red in its name. Okay, are we good so far? Did we remember all the electromagnetic radiations? So after that we have microwaves, just the microwaves that we use at home. This is how they warm up materials or like our food. I guess you don't put anything that is not food in your microwave. So I just say food, unless you do. I mean, sometimes people do in like their laboratories, they use microwaves to warm certain materials, but I think that most of us at our home, we just warm up food in our microwaves. So how microwaves work is that they warm the food with the water that is in our food. That's why you shouldn't just put a plate empty in microwave. And you have like sometimes warning signs that, you should put your food in microwave, or like your plates should have food. If you just put, plates and all that, it's not good for microwave running without food in it, because it uses the, water, it warms up the water in your food or whatever you put there. So after IR, we have microwaves, and finally we have radio waves. Okay. So remember, radio waves, you can look at it, as sitting in your car, listening to FM, AM radios, in case anyone's still doing that. I mean, I'm doing that. Most of the time I don't have reception anyway, and it takes me a while to connect my Bluetooth. So what I do, just like listen to radio. And most of the time I'm just driving, changing the channel, and I cannot find something that I can remotely, listen. And then when I just find not the best pop song, I become so happy. Okay, this is the best option, great, something that I can at least listen to. But anyway, those are radio waves that are part of this electromagnetic spectrum. And then also after that we have microwaves, and then IRs, and so on and so forth. So after that it would be just repetition to remember this. And I remember when I was growing up, it was this dilemma that whether or not microwaves can cause cancer. And I remember we had like this TV show when I was in middle school, and this professor, his name is Professor Jafarian, and then he was going abroad to study, and then people would invite him to these TV shows, is it true? Do they cause cancer? And then he was like, I'll tell you like 7 years from now, because this is experimental science. I'm like, thank you, you tell me when I realize that myself. So, and I had like a professor, the same way that I'm teaching you, he was teaching us in high school, and then he was like, microwaves are not dangerous because their energy is really low, much lower than these guys that are much higher. So that's why they are safe. That's why radio waves are safe, And there are like all sorts of conspiracy out there about like, cell phones, and also radio waves and all that. So, but for the sake of our class, and I don't make any claims about anything, I don't want like 10 years from now it to be proven that microwaves were indeed bad, I don't know. We don't have any literature that they are harmful. So for the sake of our course, what I'm going to ask you when I ask about whether something is harmful or not, I ask from like these three that we know as facts they are bad, or at least excessive exposure to them. Okay? But these ones, microwaves and radio waves, we consider them being safe and having low energies. And I don't ask you any number specifically, you don't have to remember the numbers, but I ask you which of the following has the higher energy, lower frequency, higher or like longest wavelength, those types of questions. And I think based on what I just talked about, I could, kind of help you memorize these radiations. Any question so far? Now, you may wonder, okay, we said all these things, how is it related to our course, right? It wasn't just like a break from what we learned so far. No, we're going to connect everything that I talked about to our class. So what I'm going to talk about is Bohr model. And Niels Bohr, was a scientist that came up with this model. Do you remember that we had different theories of atomic models, basically? Different atomic models or different theories about atoms. Like we had like plum pudding model, we had Rutherford model. There were like, we knew that we have protons, electrons, and neutrons, in an atom. But we didn't know how they would distribute or how are they located in an atom. And Thomson said that we have like this this negatively, so we can consider that positively a sphere. But we have like these negatively charged electrons in a positively charged sphere as like, plum pudding model, or like blueberry muffin, that blueberries are electrons, the whole cake, or like the whole muffin is, has positive charge. And then Rutherford said, no, this is not the case. We have like a, nucleus that has positive charge, and then electrons are around it, right? But we didn't exactly know how they are located around nucleus. This is, the best thing that at the time we talked about in chapter 3, right? And I told you I'm going to go back to it and then talk to you about how exactly these electrons are arranged in an atom. And to know here, first of all, please go through the slides, kind of like read what I wrote. Here, what we see is that if you have different elements, okay, and we heat them, whether giving them electrical energy or like just heat them, they emit the energy as light. So have you ever seen neon lights? This is what happens. We give electrical energy to them, and then they emit this energy to that. Oh, it is what I want. And then you can do that with different substances. This is the following, the Bohr model. And I'm going to just focus on this one so I don't distract you with the other part of the thing that I wrote here. So what Bohr said is that if I have the nucleus here, and that has positive charge, right? So it contains, again, protons, neutrons, but neutrons, they are neutral, they don't have any charge. So as a whole, nucleus has a positive charge, okay? So I write here, protons plus neutrons, okay? That constitute the nucleus. What Bohr said is that it's not like that I can put electrons around atoms, around nucleus randomly anywhere I want. They should be in a specific orbits, meaning that electron can be here, right? Or here, or here, or here, but it cannot be here, for instance. I mean, that dot became so small, but you get the point, right? Or the electron, if you have like, depending on how many electrons we have, and we learned that if we want to know number of electrons in an atom, we look at the atomic number, that is number of protons, but since atoms are neutral, that would be number of electrons too, right? Or the other one, here, right? What Bohr said was that electrons can be in these orbits, and the same thing for the other ones. I don't highlight them, but they can be in, these orbits, but they cannot be here, no, or like here, no. Okay, and then we have this ladder analogy, and I was using that in the exam last semester too, that if you want to climb the ladder, you can just, and then imagine you have like your both legs on one step of a ladder, because you may argue I put one step up, the other down. If you want to stand on them, you can just stand on the first step or second or third. You cannot stand in between them, right? I mean, some people might claim that they can. I mean, I can't, or like normal human beings, right? We cannot do that. So I gave that in the exam, and it was like, one of the options was like, we can levitate and then stand in between, and some students chose that. So for the sake of our class, and then in the scientific method of thinking, we cannot do that. And by the same rationale, electrons cannot be in between these orbits. They can only be in these, each of these specific orbits. And in the next class, I talk about this more as well. And I'm going to explain this part of the class, which is crucial for your lab in the next class. So I asked you 5 questions from whatever I just taught right now. And I'm going to give 10 points extra credit today, right after our class, to whoever can answer them correctly. And you can have one mistake, so that is fine. But in order to receive the extra credit, you should answer, at least, 4 of them. I think I gave 5. 4 of them correctly. So do your best. And you can also ask me if you have questions. Your friends can benefit from it too. So I don't mind explaining. I just want everyone to learn things.